Wow, I wonder how stars are formed.
Well, stars are formed from giant molecular clouds composed of dust and gas. They start off in equilibrium, meaning that the gravity that's pushing inwards is equal to the pressure that's pushing outwards. However, there are regions within this cloud that are much denser than others, so dense in fact that the gravity that's pushing inwards is able to overcome the pressure that's pushing outwards until collapse. By collapse, I mean gravitational collapse that leads to nuclear fusion creating the star. Well, let's take a step back. How do those density fluctuations even occur? Well, the gas is in constant turbulent motion, which is chaotic motion. Let's take a deeper look. This turbulent motion compresses on the gas, which leads to those density fluctuations. There are two types of turbulence in these giant space clouds. The first is solid turbulence, which primarily consists of swirling motions and vortices. This does not lead to any significant changes in the gas density. However, the second type is compressible turbulence. This involves the expansion and the compression of the interstellar gas, which leads to those density fluctuations.
I wonder if I can distinguish between the two.
Well, let's take a look.
I decided to start with simple, using Google's Teachable machine, which uses a convolutional neural network. Convolutional neural networks, or CNNs, are a type of deep learning model primarily used for image recognition. I trained it and I tested some data. For instance, here's an example of solenoid turbulence. And here's an example of compressible turbulence. What do you think this is? Well, the AI thought that it was compressible turbulence with 100% certainty, when it was really solenoid turbulence. Here's a quick demo of the webpage I made as a part of this project. This project could not have been done without the paper comparing the statistics of interstellar turbulence in simulations and observations. Solenoid versus compressive turbulence forcing. My conclusion was that I wasn't able to understand the flow of turbulence, but rather the appearance of turbulence. Even with this in mind, it was impressively accurate at distinguishing the compressible turbulence, with a 95% accuracy. Moving forward, I'm excited to explore how physics-informed neural networks would perform the same in this project and how I could incorporate them. Thank you so much for watching, and let's learn by building.